Good evening. Welcome to another wonderful talk in our public MBA series. Today I would like to thank our supporters from TT Tech. TT Tech is a neighbor of us. TT Tech also supports the MBA. We had a workshop with them for Module 2. We had also a workshop for the last cohort. And today we thank you for supporting this talk and for inviting our guests, Xavier de Kestellier. Xavier de Kestellier. Yes. Matthias Mackail from TT Tech would like to say a few words to you. And I give you the micro before I introduce our guest.
Thanks a lot. Welcome. Good evening. I will just spend 1 minute to explain why we support a public lecture on interplanetary architecture. The reason is simple. We work ourselves as a company based in Vienna, but with offices in Houston, amongst others. We work on several habitats. And more or less now, the known habitat right now is ISS, but there will be commercial successors which are planned. And then also there will be a lunar gateway, which will take shape soon. And we work heavily with equipment like this on the lunar gateway. And this basically is just an image that represents the lunar gateway, which will be a flying orbit that includes 2 habitats. A European one called the Lunar IHAB and an American one, which is called HALO, Habitation and Logistics Outpost. And we also work with an Italian company on a multi-purpose habitat that is really cool, that is on the lunar surface, and it is a bit like a caravan. So that's our connection to various habitats that, of course, require architecture and a lot of engineering to make them safe, because the main issue in space for most people is radiation. Everything else is not as trivial as radiation. Radiation is really the issue. That's why we need a lot of fault tolerance built into all the habitats to make sure the people survive in the first place. Thank you. Very happy to support this lecture series on habitats.
Thank you very much. Now I have the pleasure to introduce our lecturer, Xavier de Kestellier. It's so hard to pronounce his name. Xavier de Kestellier is an architect by education, but he's also a technologist. By profession, he is the head of design and innovation from Hassel Studio in London, but also worldwide in the corporation. Xavier has worked on a number of large-scale projects, because Hassel Studio is a global company, international company, with more than 700 employees. He has also worked for Foster and Partners before, also on large-scale projects. But the reason why he's here today is because he is one of the space architects in Europe that has really given space architecture a public face. The drawing, you will see images from the projects. The projects that he worked on are, I would say, the most famous ones, the most cited ones, not only in Europe, but we are glad to have him in Europe, but also worldwide. So his work is kind of spanning our architectural profession, with engineering background, with the technology know-how. He also works on immersive environments and virtual reality, and all this put together he calls Adventures of an Interplanetary Architect. And I wish you a safe and enjoyable journey today, and thank you for coming, Xavier.
Thank you. I'll have this one. Okay. Should we just move this one? Yeah. Okay, everybody hears me well, loud and clear? I'm sorry. My German isn't that very good, so I'm going to do it in English, all right? So yes, I'm an architect. So how did I end up, being an architect in space? It's not very common to do that, right? So for me, it all started when I was about 12 or 13 years old. My dad took me to an exhibition in Brussels. And the exhibition was about space. And it was quite an amazing exhibition. Because I was quite a fan of space. Because it was in a big hall, and there were lots of big modules they brought in. Actually, 1-to-1 scale things. You have to remember, this was at the end of the Cold War. So we had the Soviets bringing in stuff, the NASA bringing in modules to kind of show off what they had. I remember there was a big blow-up space shuttle. I wasn't quite impressed by that. But I was impressed by one thing that was there, and that was this. This is actually a module, a training module of the Mir space station back then. At that point, Soviets had their space station going around to Earth, but I was able to kind of step inside that module, right? There was the training module that the cosmonauts were using to train in, but it was there, and I could touch it, and I was kind of, this is incredible. Just the fact that I was able to touch it and almost, think I was a cosmonaut was incredible. So I went home, and what I did, at that point in time, my sister, she was at university studying geography. So she had a drafting table to draw maps and rapidograph pens. So I kind of took her stuff, and I started to make drawings, spaceships. But they were not sci-fi Star Wars spaceships. No, I kind of, weirdly enough, started drawing these technical drawings, these technical sections of spaceships, and tried to make them as realistic as possible. I even went very nerdy. I did the wiring of the spaceship as well. So that's why you think my career started as a space engineer or a space architect. Well, of course, I didn't think that was a job or that was a career. So I did the closest thing to it, and I became an architect. So for the next 15 or 20 odd years, I worked on projects like these around the world. First at Foster & Partners in London, one of the largest architecture firms in the world, and now at Hassel, also a super large firm, a global firm. And that was kind of the projects I was working on. Often what I specialized in was complex geometrical projects. As you can see, all the kind of like the funny shaped buildings, right? And some of them quite famous, I think. This is the Apple headquarters in Cupertino. And the top left one is Beijing Airport in China. And maybe some space-related stuff. The top right one is Spaceport America in Nevada, where Virgin Galactic was having spaceships taking off, or trying to. But for me, I was very lucky then, it's about 15 years ago, something like that. I had an opportunity, and it was kind of quite at random. I told the story to the students this morning. I got in touch with a company that was doing 3D printing, and they had a contract with the European Space Agency to test out 3D printing on the moon. So do some lab testing of taking regolith, lunar dust, and see if we can 3D print with that. That was the research project. But we took it further, because we're architects. We wanted to say, well, what is it going to look like? And then we'd make these images. And something we've been talking about, how these are an image that is quite famous out there, that people use quite a lot. And you see the initial ideas there. What this is it's a dome. It's of regolith, of lunar dust to protect the astronauts, right, from radiation mainly, and micrometeorites. So that was the first project. Now I moved to Hassel quite a few years ago, 8 years ago, and this is where I really started to work on these space projects. I have a small team. It's called the Design Innovation Team. And what we do is look at new technology, new ways of building and new ways of designing, and we test it out on smallish projects. And these projects are not always in space. They are always in extreme environments. So these extreme environments can be anything from a glacier in the Swiss Alps to a beach in Senegal or to a refugee settlement in Uganda. But of course, quite a lot of space projects. And this is the ones I'm going to talk about here today, mainly about the space projects. So I'm going to talk about 3 projects, really. The one is kind of related to the other one. There's one on Mars, one in Earth orbit, and one on the Moon. So let's get started with the first one. This is a project, it's the 3D printed Mars habitat competition. It was a competition for NASA, run quite a few years ago now. And the question by NASA was, how should we build, how should we design on Mars? How should we use 3D printing as a technology on Mars to build our habitats? As an architect, whenever you design something somewhere, you always go and look at precedents. You go and look what has been built before. So what has been built before in space? Well, the International Space Station. And as an architect, you look at these things from an architectural perspective, from a critical perspective. When you look in the International Space Station, that's what it looks like. I'm not sure about anybody here, but would anybody want to live in a house for 6 months that looks like this? No, right? Thank you. Absolute chaos, wires everywhere. It's an absolute madness to live in a space like this. And I just still don't understand. This is the most expensive building in the world by square footage, right? But it doesn't seem we had an architect involved in it, which is, I think, a very weird thing to do, right? Because I think here you're just part of a machine, right? The humans is part of a machine. They're not central. I often get the question of people that say, oh, space architecture, so where do you get your inspiration from? And they say, oh, maybe movies or sci-fi. And although, I love sci-fi. I think they're fun to watch. That's not where the inspiration comes from. Because these are just backgrounds for a narrative, for a story. They're not the real thing. So I often look at people that came before us, architects in the past and designers in the past, and there have been in the past. This woman, for example, Galina Balachova. She was the only female architect in the Soviet Space Agency. Actually, I think she was the only architect even in the Soviet Space Agency that worked. And her work is quite impressive, I think, because she gave it a completely human angle. And she was able to make beautiful drawings as well. This is one of her drawings, the aquarelles that she made, of the Soyuz orbital module. This looks very different than the International Space Station. This looks very homey. There are some wooden veneers. There is even a little curtain. It looks much more comfortable immediately. This was never built, but some of her work was implemented. This is the Mir space station, the one I got as a 12-year-old really inspired by. And Galina worked on this project. She actually worked on the color scheme. So they had this idea to put certain colors in to kind of give the cosmonauts a certain orientation. So the colors, actually, the green is always on the floor, for example, because you're in microgravity. Like floor, ceiling can be anything, right? But the colors gave an orientation for these cosmonauts. Okay, another important designer in space. This is Skylab, 1970s. This is the first NASA orbital station around the Earth in the 70s. It just came after the Apollo missions when they had some hardware left, some modules left that didn't go to the moon. And they reused and refitted those out to be orbital stations around Earth. The person that got involved, the designer that got involved, was this guy, Raymond Loewy, French-American industrial designer, really famous back then, and that got him involved. But these NASA engineers were a bit skeptical They were, what is the designer coming to do? What we do is rocket science. This is the real stuff. Like a designer, what is he going to do? Maybe choose the colors or something like that. He did choose the colors. That's one thing he did do. But he did a few other things. First thing he did was design this table. So this is 3 astronauts having a meal in Skylab around this table. And he designed the table. You might think, okay, it's a nicely designed table, looks very functional. What's so special about it? Well, in the original design, the engineers decided to have these little kind of folding down tablets in different locations in the space station. There was one over there, one over there, one over there. So during a mealtime, these astronauts would be in different locations, facing the wall. So imagine that these astronauts would not be having a conversation about how their day was, how it all went. So yeah, they needed a designer to kind of convince everybody they needed a table. Second thing is the window. Again, you might say, the window in the back, the round window, what is so special about the design of that? In the original design, NASA engineers thought having a window is a structural weakness in the structure, in the shell. So why do that? Why do a window? And Raymond Loewy was very kind of, strong in his thoughts about it, and he really pushed him to put a window in the end. Because imagine, you are a NASA astronaut, you're going around in the first orbital space station, and for weeks around Earth, and you never see this, right? That, for me, is lunacy, right? So, so these are the people I kind of look up to and kind of think about when we design our habitats. Okay, back to Mars, back to this NASA competition. When you design for a different planet, or when you design anywhere, even on Earth, the first thing I do is look at the local environment. What is there? So, first of all, the distance. This is the famous Earthrise picture, taken from orbit, Apollo 8, I think, around the moon, looking back to Earth. It's about 3 days distance, not that far. When you take that same picture, this is taken from the surface of Mars. That 1 pixel that you see there, I hope you see it, that is Earth. The distance is 1,000 times, or more or less, the distance Earth-Moon. So it takes a long, long time. So anything you're going to take, I always say when you go to another planet, you better pack light and compact. So make sure whatever you bring is not too much. So let's think about that. And then the surface on Mars. There's the surface. The environment. Let's talk about that. It's about the gravity is 1/3 of Earth gravity. So when you jump, I can jump 3 times higher. When I make a structure, I can make it 3 times thinner. Kind of fun for an architect to do. Temperature fluctuates, let's say, -40 Celsius. Atmosphere, better than the moon. It does have an atmosphere. But it's a very thin atmosphere of CO2. So that's okay. It's one of the issues that we have on Mars is there is no electromagnetic field around the planet. On Earth, we have that. We have a beautiful electromagnetic field. What does it do? It protects ourselves from radiation. Our atmosphere, our thicker atmosphere, and the field protects itself from radiation. We don't have that on Mars, so that's a bit of an issue. Anything else? No, I think that's it. That's our environment, our environmental factors. And whenever you build anywhere, it's always good to use local materials. Now, anywhere on Earth, if you're in Austria, in the Alps, you're going to use lots of wood. And whenever you are, use the local materials. What do we have? Not much. We have regolith, which is dust, Martian dust. That's what we have. This was our main concept. We're going to bring something light and compact, which is that kind of inflatable bubble. Right? The inflatable. That is something we're going to bring from Earth, made on Earth, inflated on Mars. and that will be a pressurized volume. Our astronauts will be able to breathe there, temperatures are regulated, and so forth. The one thing it can't protect our astronauts from is radiation, solar radiation and cosmic radiation. For that, the best place to be on another planet like Mars would be in a cave. The best place would be go and live in a cave, because you have lots of mass around you and protects you from radiation. We don't have that cave. We don't know sure where they are on Mars, so we're going to build our own, and that is this shell structure that you see around the inflatable. It's purely there to protect the astronauts from radiation, harmful radiation. And this is how it gets built. Looks like termites, but they're not termites. What they are is a swarm robotic system. It's being 3D printed, layer by layer, this kind of cave-like shell structure. This is it. And underneath it, you get these inflatables. This is a physical model we made to kind of explain that. So we create our own cave. Now, I do like to use some references always, because this cave that we have there is made out of 3D printed regolith, which I kind of compare to really terrible concrete. You know, that's what I would compare it to. So to make anything out of concrete without any reinforcements, without steel in, because we don't have the steel, we need to design in a very particular way. We need to design so the shell structures are under compression only, right? An architect who actually used these ideas is Antoni Gaudi. What he did for the Sagrada Familia and other projects is he used something what's called a chain line or a catenary structure. He actually designs the buildings upside down. So this is a model, a physical model of, I don't think it's a Sagrada Familia, it's another building. And he actually puts little weights on it. And that geometry, if you would take this building upside down, that would be the perfect structure. Now, we advanced a little bit since Antoni Gaudi. We have digital tools. So here you have a little model that is defining that geometry of our shell structure. I did not draw it. I had the computer designing it for me. I gave the parameters, and then it was a form-finding technology that actually allowed me to find the ideal geometry of this. These are the robots, you know. I made these up a little bit. Some of them I didn't. Like the one on the right, there's the Razor, which is it's something that has been developed by NASA already as a digger from the moon or on Mars. And I was quite happy. So some of them kind of go and look for the regolith, other robots go and collect it, and other ones 3D print it. So it's a kind of a swarm robotic system of different robots having each different tasks. But this was the rendering I got from my visualizer, from the artist. I was very happy with it. I think it's beautiful. He really wanted to show me what it would be to live on Mars. Except this shocks me. Because what you have there is these robots, these swarm robots that done their job. They've built the shell structure. All done. Nothing to do now, so I can just throw them away. And I'm thinking, oh, this is a wrong thing to do. I can't just bring heavy equipment to Mars and then use it once for one job. This is a ridiculous idea. So we thought, okay, back to the drawing table. And we did this. We redesigned them, and redesigned them as a modular system. So there's wheels, there's batteries, there's solar panels, there's diggers. And the idea is that we, with these almost kind of Lego block robotic elements, can each time make a different printing module or a different function, right? There's a digger, there's a microwaving the regolith module as well, and you can see that. So this is the one that goes out and scouts for the right regolith. This is the one that goes and digs out the regolith, and then we have them going and printing it layer by layer. And it does this by using microwave technology. You might think, well, Xavier, this is all a bit sci-fi, right? Is this really real? Well, of course it's not real. But the way we work as architects and the way I like to work is we always look at technology that is kind of out there, that's being researched already, that has been developed in universities. And yes, people have already used regolith or simulant regolith, so a similar material, and tried to microwave it, and it did work. So yes, there's no robots yet that can do this, but it's not sci-fi after all. I do like to go and try stuff out as an architect. Go and build stuff immediately. This is a workshop we've done quite a while now at Smart Geometry Conference, where we went out with a bunch of architects and tried to build our own little robots, right? It's kind of a Lego kit system that we used, which was really, really fun. And we learned quite a few interesting things about that. Now, this is the habitat. So we have the shell structure, and underneath we have these inflatable modules. There's 6 modules, and they're connected by the connector modules, which are smaller, right? Oops. Okay, there we go. So how do we organize this? Like I said, I like to be critical. I'm an architect. I have to be critical. So I'm also critical on the ISS, on the International Space Station. This is the Columbus module on the ISS, and it's a classic module, right? You have a cylindrical module, right? A cylindrical shape. Why is that module that size? Well, that's probably the size that you could fit inside the space shuttle when it was, there you go, the rocket, right? And the size, the fairing of the rockets. That's why it's a cylinder. It's also good to kind of hold the pressure, because it's a cylinder. And then inside, what happens is you always keep one direction up. You don't do, so there is still a ceiling and a floor, and there's some sidewalls. The sidewalls here are always science modules, these racks. And the bottom, you'll have storage, and the top, you have storage as well. Now, weirdly enough, the International Space Station is really, really big, and it's actually just mainly corridors. And it is because you kind of have these science racks where these astronauts are going to set up an experiment and then goes away and leaves it. But actually think about this. The space in front of it is not really used then, right? So from a spatial perspective, I don't think it's ideal. So you can look at then, and I often kind of look at just simple architectural solutions for things. This one, a mobile shelving racks that you can find in archives, where they're very, very space efficient, because you can open them up, you go inside, do something, get a book, come out again, close it again, right? And so we thought, it's interesting to experiment with that. So that's what we did in our habitat. We have these radial systems, radial pods, and each time with a rack that is able to move. And we can do that it's very modular. You can do it for a lab, you can do it for a greenhouse, and so forth. And it's very modular because you can then swap it around. So you can make the greenhouse suddenly into a lab if you want to, and switch it around. So, and it all comes flat packed. It's kind of IKEA system, right? A space IKEA system where you can take these racks, bolt them together, put them on a rail, and able to kind of move them around manually, really. And we have 6 of those pods, then all connected with suit ports. So if you can get out, you can get into your suit. It's a suit port, and a rover as well. So you can get out in different ways onto that Martian surface. And here we have it, the lab. Here's our astronaut working away. And then when he's finished, he can actually come out and close that off again and go in another rack. Or same thing with the greenhouse. You can do that too. Now, remember, we need to protect our astronauts from radiation. But at the same time, just like Raymond Loewy did at Skylab, we want to have a view out. There's a view out on the ISS at the moment, the cupola. It's an interesting thing, because it took 23 years for the cupola to be from design to installation, because they always got cost engineered out. It was, well, what is the real necessity of it? But now it's been installed. This is the picture where all the astronauts take pictures. This is the place where the pictures are taken. This is where the astronauts hang out, where they look at Earth. And I think it kind of, if people think of the International Space Station, that's what they think of, right? That's that image that they have in their head. But it's a trade-off. They also need to protect the astronauts. So if you look at the outside of the cupola, they've got these flaps that they can close it off, for protection. This is a very mechanical way of doing it. And we thought, is there a better way of doing that? Maybe a more architectural way. And the way we thought of it is as a courtyard. Think of a courtyard, maybe in Morocco or something like that, where you have a courtyard buildings. The great thing about those is that you get light in, you get daylight in, but you don't get direct sunlight. Same thing here. We get light in, we get views across into our habitat, which is interesting, but we don't get direct sunlight in, which equals radiation. And you can see that here. We had to trick our radiation software that we use on Earth to work on Mars. And you see the little white circles there. They're in the blue. They don't get actual direct sunlight. This is what you get then. So this is our habitat, our living space, looking across to the other modules through that courtyard. Now, you might remember that I said we're going to pack light and compact. Well, look at the furniture. Not exactly light and compact, I would say. So why did we do this? Well, we come up with the idea that we maybe going to print these chairs and sofas in space. And the idea was to use it because we will have waste materials. Right? We're going to have lots of plastics, waste from food packaging, for example, or from experiments or anything like that. What are we going to do with that waste? Well, maybe let's just 3D print with that. Again, I don't just want to make a picture. I want to go and try it out. That's what we did. So we worked with a company called Nagami, and they have a company that 3D prints furniture. They're using PETG plastics here. And we tried it out with them and said, design is a chair that would be great, or a chaise longue in this case, that would work on Mars, or that we can print in our habitat. And that is this. As you see, it looks very spacey. I always think it looks very spacey, but it is because the whole thing has been built of one kind of line of PETG melted plastic. So just one little line. So to do that, you need to create something actually that's quite organic of shape to be able to create that. And there you go. A rather spacey looking chair. Not on purpose, I always say. But we started to think, as an architect, you think about the furniture and everything that is there in the habitat. And I started to think, what are they going to wear, our astronauts? So at the moment, the astronauts in the ISS, the clothes they wear, after they're dirty, they don't wash them. There's no washing machine in the ISS. They just get rid of them and get burned up with the next module in Earth's atmosphere. Not very sustainable, I thought. And what are you going to do when you're on Mars? You can't really do that. So we started to think about this. There is fabric on Mars because lots of the modules and the rovers, in this case, Perseverance rover, when they land on Mars, they have a parachute. It's single-use material. It's only used to land, and then you don't do anything with it. So we started thinking, wouldn't it be interesting to start imagining what these astronauts would be wearing? Maybe they kind of reuse the material, the parachutes. Luckily, I know a guy who does that. Friend of mine, Chris Rayburn, he's a fashion designer in London. He has a label called Rayburn. This is in his lab, and that's what he does. He actually makes clothes of overstock of material, of old materials, of old parachutes, or old blankets, or anything like that. That isn't materials that aren't, textiles that aren't used anymore. So, and actually the jacket I'm wearing today is made of an old Japanese parachute. So we worked with him on some pieces of clothing that we then used to imagine what our astronauts would look like in our space station. This is us using a little green screen in the studio. This is not an astronaut. This is Chi, one of our interior designers. But for that day, she was the astronaut. being in a very important space. This is the workshop. And we like to put little details in there. You see, there's a sewing machine there, right? Because they just made some new clothes. There's a 3D printer in the background there making some new furniture. Because I think that's really important. Once you're in space, you can't order a new part. It's not like the International Space Station that it can send up new materials. Here, they will need to fix it themselves. So a workshop, really important part of the habitat. We're very lucky that for this project, right at the end of the project, there was an exhibition happening at the Design Museum in London. And they wanted us to design one of these habitats. So visitors to the museum, the Design Museum, could really feel what it looked like. Go and sit down, look across the courtyard and see the other habitats. Well, this was, of course, a big digital screen. And just kind of imagine what it would feel like to be an astronaut on Mars. I think I still have enough. Yeah, I'll do it. A little bit of time. We did make a video as well. I'm going to see if I can play that now. See if that works.
We took our first step on the surface of the moon. Today, there is renewed passion to explore for our next human endeavor.
Is that loud enough?
Mars, the red planet, further than any human has ever been. We face many challenges: remoteness, no livable atmosphere, high radiation, dust storms, and extremely low temperatures. Before any humans set foot on Mars, we must first design a protective shelter. We will protect our astronauts from radiation with a thick 3D printed shell structure using Martian regolith, which works great in compression but does not perform well under tension. To overcome this shortfall, we have chosen to construct the pressure-retaining parts of the habitat from lightweight, inflatable pods. They will be made out of high-precision engineered composites that are prefabricated on Earth. Their elliptoid geometry will be able to mitigate the pressure differences whilst optimizing spatial planning. To create the base on Mars, we will use a two-phase approach. In Phase 1, an ecosystem of 3D printing robots will arrive months in advance of any human explorer. They will construct the protective shield for the base by adopting a modular robotic swarm strategy, a plan that allows for redundancies and enhances the odds for success. Intelligent autonomous robots will have interchangeable roles, from battery storage to scout rovers, logistics to excavational, and even 3D printing units, all integrated with multiple cameras and sensors for navigation. They can reconfigure themselves for a multitude of purposes, ensuring prolonged usage beyond the initial build phases. The smallest configuration is the one-wheeled scout rover that uses ultrasonic scanning to analyze the Martian surface to determine the best regions for obtaining optimum regolith. The digger receives the location coordinates and then excavates the Martian soil. It then delivers the payload to the refining assemblies. Here, large chunks of Martian regolith can be processed down to a finer grain and then delivered to the melter robots in situ. They then use concentrated microwaves to melt the regolith and extrude through the 3D printing nozzle. The shell is autonomously 3D printed, layer by layer, over several months by the robotic system. In the next phase, the first astronauts arrive with the habitation units, equipment, and supplies. The robots now take on their second life roles to aid the next phase. They come together to make flexible mobile platforms that can carry the payload from the loading zone to the base. The convoy begins its journey across the Martian surface to the habitat site. The build commences with a connector module placed underneath the protective shield and ready for inflation. The module then unfolds and self-inflates into its final form. The habitation units are then placed into position and sequentially inflated to form the completed pressurized environments. The circular layout of the habitat ensures continuous accessibility of the habitat in the event of a catastrophic failure. Each connector module houses 3 integrated environmental control life support systems, delivering essential services like power, water, data, and oxygen to all the habitation units. A circular conduit delivers these services to multiple endpoints in each pod. The base will be remotely powered by 2 nuclear kilopower reactors and a solar farm. located a safe distance away from the base. In the next stage, the astronauts will construct and install a flat-pack, rail-based racking system capable of connecting to the distribution system, enabling spaces to reconfigure according to their spatial needs. This modular and radical design principle has been adopted for all the habitat pods, ensuring multi-use, reconfigurable environments. A Martian base should not just be a habitat. It is home for the astronauts. Each pod expresses its own identity, quality, and character. A highly functional design which places the human experience at the core. Spaces include a state-of-the-art research laboratory, a hydroponic greenhouse, a fully equipped workshop with digital fabrication facilities, the sleeping quarters with gym facilities, and immersive virtual reality platform. We believe that the key to success of human habitation on Mars is the health and well-being of its residents. Creating a place where work, life, and living combine holistically to ensure they feel connected to each other, to themselves, and somehow to their distant home.
Okay, next project, right? 2 more. We're not on Mars anymore. We're coming a bit closer. So this is a project for orbital reef, it's called. The International Space Station is getting a little bit old, and just said there are new space stations on the way. They are being made, and commercial space stations, so not run by NASA or ESA or anything anymore. So this is one of those commercial ones. Orbital Reef is a collaboration between a few companies, but mainly Blue Origin and Sierra Space. So we worked with Sierra Space on one particular part of this habitat, which is the life habitat. What you see about this one is it's kind of interesting. It is an inflatable. So a bit like our Mars habitat, it is an inflatable. And you might think, well, this sounds a bit of sci-fi still, doesn't it? Inflatable habitats. Well, not really. Since the 60s, NASA has been working on inflatables in space because it makes total sense. You can compact it when you fly it up, when you launch it, and once in space, you inflate it to the right size. There is actually a module on the International Space Station already. It's a test module that actually is an inflated part. So it's not sci-fi. It is quite realistic. So we worked with Sierra Space on this one, which is orbital reef, well, the life habitat module. It was a fascinating project because we were given already the volume, right? It's a bit like an architect, and they go like, well, this is the size of the building you're going to design. It's already there, right? And we had 2 parts. We had this kind of longitudinal part here, and you see there, that is actually a hard shell, which is made out of aluminium. And then you have the big one, which is an inflatable. I think in the original design, they fitted it out in a completely different way. But we came out with this idea. First of all, the hard one, the cylindrical volume, it wasn't like the Columbus module I showed you from the ISS. You weren't really standing up in this way. It was too small. So we decided to say, well, if it's too small, we'll just make it a vertical volume. We're in space anyway. We don't need a ceiling or a floor. We don't need to stand on anything. So that's what we did. So we made this volume a vertical one. So the astronauts could pass each other, right? Because it was still some practicalities around that. And there was also a window in that one. So we added that. Then the other module, which is the inflatable one, we thought, well, it doesn't matter which orientation you are in space, of course. So we thought, well, what we'll do is we make a mirror. So we mirror the spaces. So what you see is the astronaut going up direction is that way for that volume, and for that volume it is that way. Because you do want to keep an orientation in a volume, right? Otherwise it gets really disorientating for the astronauts if you say, well, anything can be a ceiling or a floor or anything like that. No, you do want to keep an up factor in a way. But if you change space, you can change that. Right? So we thought, well, let's do that. Let's make these spaces mirrored, and in between, there's It's not really innovation, it's kind of a raised floor where we put all the technical systems in. You can see it in the middle, number 4. And we thought, let's make it also a bit neater. So we did look at very interesting storage systems, that everything was more hidden away. And in the end of the day, a space, hopefully, where our astronauts want to spend a longer time. Because, think about this. At the moment, lots of the astronauts are professional astronauts. They trained for years to do this. In the future, we'll have people that are space tourists, that only had a short training, spend a few days there. You'll have maybe researchers as well. So a much more diverse set of astronauts will go up. I think for that reason, we also need to make sure we get much more comfortable spaces designed. Last project. This is the one we did a couple of years ago, one launched last year. It was the European Space Agency Lunar Master Plan. Now, this project was a research project, and there was 2 things we wanted to do. We wanted to see how would it be if we design a habitat not for 5 or 10 astronauts, but maybe for 150 astronauts. How would we do that? And I wanted to do rectify 2 mistakes I've done in the past, right? This is the project at Foster's, where we had this one habitat, and then in the video, because we made a video of this one as well, in the end, we just added a few more, right? Because it's growing. You add a few more. We did the same thing for the Mars one you might see in the video. We just did one, and then we add a few more. Because it's growing. And we'll do that for 150 astronauts. Well, no, I don't think that is right. Because cities are not built like that either, right? It's not by just adding more urban sprawl in the US, more buildings, that you suddenly create community, where you suddenly create great cities. Great cities, like one of my favorite cities, Barcelona, they are built through master plans, right? By a system that is set up, and within that system, within that master plan, different things can happen. Different things can be adapted and changed. A master plan is also not defined from the start. You don't decide in a master plan exactly what building is going to go where, but you give a guideline, right? And of course, in Barcelona, that's done by CERDA's master plan. So I was thinking, what can we do for a lunar base that is similar, that gives a guideline, that gives a structure, but doesn't define everything yet? Because we don't know what that lunar base will be, on how it will grow. We do like to look at extreme environments. This is McMurdo Station in Antarctica. That is kind of grown quite ad hoc. They built something, they added something extra to it, added something extra to it. There was no master plan, really. There's other projects in Antarctica, though, that do have some sort of a master plan, an overall idea. This one, Halley 6, from the British Antarctic Survey. I think this is an interesting project because it just has an idea what it could be and how it could grow in the future. So we had to make our own master plan. That's what we did. We have this idea of these inflatable modules that are all connected. Because of course you can't just go outside to go to the other building, right? When you're on the lunar surface. So they're all connected. You get from one space into the other one. Oh, sorry. But there's one problem with that, I always think. If you do that, if you go from one space into the other one, if I go from one side of the master plan in that module up there, and I want to go to another one, I need to go through every other space. It's a bit like being in a street. And you go from one building to the other building on the end of the street, and you walk through every other building. That is just a bit weird, right? So we thought, what are our streets? What are our streets on the moon? We're looking at this, skywalks in Minnesota. In Minnesota, because when it gets really, really cold that winter, people don't go outside anymore. They have these kind of connections that are on the second or third level most of the time. It's like an extra street system happening, but it's hovering above. So that was our inspiration then to do that for our system, where we have 3 levels. The lower level is where your astronauts live, where in the modules, all connected. The level above is where you get out in the lunar surface, where you have suit ports, where you have rover connections. And the 3rd level is then our skywalks. It's when you can go from one part of the base to another part. You see the blue ones. They're out above. So these lunar modules, right, these kind of shapes are kind of our master plan. These are our, let's say, our city blocks almost, right? And within those, many different things can happen. Now you see this geometry is quite different than the one we did on Mars. On Mars we had these round ones, right? The round radial ones. I personally find it very difficult as an architect to fit that out, to kind of fit square stuff in something round. It's very difficult. But you need it round because you want to take up the pressure difference, and curved geometries are very good for that. So how can I get something that is square but round? Well, there's this shape. It's a pill shape. So the nice thing about this one is in the middle you actually get geometrically quite a rectangle space, which is easy to fit out. You can put square racks in it and all that. We had different sizes of this, and you can see these kind of different flexibility and adaptability of the racks, because a lot of the stuff will be racks of science experiments and all that. So, and this is our standard module, right? This is our 6 bedrooms, small living room, and all that for our astronauts. So this was kind of the main standard volume. But we decided that we wanted to test out many other different functionalities in that same geometry. And we found that quite a good grid to play with, because as you see, we could come up with many, many different other functions. Greenhouses, restaurants, storage, labs, and so forth. Greenhouses, all of that was able to kind of fit within that one geometry. But we'd like to go in a bit of detail immediately. Yes, this was a master plan, but I'd love to go and zoom in just quickly and start to understand what it might look like. And we wanted to make this a lot more comfortable for the astronauts as well. Use some more tactile materials. Like you see, these looks like, well, these are actually bamboo veneers. So we're thinking it might be the astronauts might be able to grow bamboo in their base, not just to feed yourself. You're going to grow stuff to feed ourselves, but maybe to build with. So locally built bamboo might be used for that. We're even thinking the sofa, we're even thinking maybe it's grown out of mycelium, right? So starting to have these ideas what this kind of space aesthetics could look like. If you have 150 astronauts, what do you need? You need a bar, I think. So we designed our lunar bar. So we thought, what would this lunar bar would look like? And there are some clues in there. There's, first of all, yes, we have some 3D printed furniture. But it might also be important to start recycling and reusing elements. And you see, yes, you see some nozzles there from rockets or something like that reused to a coffee table. And even although this won't be possible, let's reuse the seat of the Apollo rover, right? But we won't be able to do that. But just to start thinking, we need to start recycling, upcycling materials. Oh, and the bar. See the bar in the background? These bags. Well, of course, we're not going to bring bottles with drinks with us, right? That would be too expensive. So yes, they would probably be in bags, hanging up. Just a little bit of a different idea. And this is kind of us starting to think how we could design with local materials and local, requirements. The inflatables themselves, we actually found an interesting analogy or a structural system. This is a tensority structure. Now, a tensority structure works an inflatable having with, this for the structural engineers in the room, a small compression element on top and some cables in the bottom. It's a very, very lightweight system to create a bridge or a structure. This is a Montreux in Switzerland, which is a car park, and this is another bridge. The problem is with this system is the moment you don't have air pressure, the structure kind of collapses, so it's not really a great thing. So on Earth, it's not a great solution, but our modules will make sure they're always pressurized. So we came up with this idea that our volumes have this system of compression and tension cables. So they're kind of like bridges. They only need 2 legs either side to actually touch the regolith in as minimal as possible, because the regolith itself is a very harsh material. So we wanted to kind of stay away with our inflatable modules as much as we could from that regolith. How would it grow? Well, it should probably only have, for 6 astronauts, it maybe has just 3 modules. And then it could grow for 150. But how it would grow, we don't know yet, and we don't want to know. So we came up with different scenarios of, well, maybe it's mainly tourism, or it's maybe commercial. So we came up with different scenarios, but there's millions and millions of scenarios possible. But we don't actually care about that. For us, it's having a system in which this whole base can grow into. It's just having a master plan in the end of the day. Almost there. We also started to think, 3D printing these shell structures, that might be quite tricky. You know, I've done concrete printing projects here on Earth. It's very, very tricky to do. So maybe we build our shell structures. This is a beautiful example at the Venice Biennale from a friend of mine, the Block Research Group, which is this shell structure made out of stone. But the problem with these systems is, and the way we build buildings on Earth, is that we have high tolerances. We need to be extremely accurate building these buildings, these constructions. On the moon, that might be quite difficult. So I was looking at systems that were not very accurate. Can we find ways of building stuff? This is Cora Dierichs with an aggregate pavilion, which is just kind of spiky elements that are just thrown on top of each other. And they kind of somehow structurally work. I'm kind of inspired by that. It was interesting, I thought. And we also saw this pavilion at the Venice Biennale made out of salt, these kind of interconnecting little X-shaped geometries. Made me think about something. Maybe think about these coastal barriers to stop erosion happening. They have a very particular geometry. And I was wondering, could we use that to really start and build our caves, our shell structures under which these astronauts would live? Because that might be a much easier way to do. And we don't have to be accurate. We can almost throw them on top of each other. This is digital simulations we use. Many of those we did. And we kind of settled for this one, where you start off with some foundation of these tetrapods. The geometries, we call them tetrapods. Right? It's little star-shaped elements. But they need some good foundations. And then in the middle, we place an inflatable, a big inflatable. This is not the one where the astronauts will be living in. This is purely scaffolding, right? Only used to build with. There's some kind of beams as well. And then we start throwing these elements on top of it. And when I say throwing, I actually mean it, throwing. Because we have 1/6 of gravity on the moon. So to throw something, it's much easier, right? And the impact an element will have when it lands will also be less. So we actually don't really care exactly where these elements drop. They just have to kind of fall and they'll interlock with each other. Once that is done, the big inflatable gets taken away and we put our inflatables, our pill-shaped inflatables, where our astronauts would be living. And then we cover the whole thing. We keep on covering that. Now, of course, you might say, well, that's all good. You made some renderings of it. You made some digital simulations. That's easy to do. So we did try it ourselves as well. We printed a whole load of them. I bought a yoga ball on Amazon, nailed it down, and quickly we started to try out if this could work. And it kind of did. And this is I think I'm near the end now, am I? Oh, yeah, I'm near the end. So this is how we are now. This is a model we made, a physical model we made of how we're thinking on the moon. We might do it slightly different than on Mars. Now, all these projects, the nice thing about these is that we always try to learn from one of the other. So they're not being built yet. Yes, I know. It's still a bit in the future. But I think a process of design where you go and test things out and then learn from your own mistakes, which I've done with all these projects, and continue that kind of quest of coming to a solution that would be more and more feasible. Thank you so much. I think we do questions, yeah? Any questions, anyone?
Thank you for the very inspiring presentation. One question about these tetrapod-based buildings. Wasn't the main idea of the dome to protect from radiation? How well would a porous dome, a quite porous dome, protect from radiation?
Good question. Also, you might have noticed our little skywalks don't have protection at all, right? Why is that? Because it's not that you need to protect yourself from every bit of radiation. You know, we're getting radiation now, right now. So you have to limit it, right? So if I just walk from one part of the base to the other part, I spend maybe a minute doing that. Doesn't really matter, right? Where it does matter are the areas where I sleep, for example, where I spend a lot of time. Or where when there's a solar storm happening, radiation, really high levels of radiation. So one of the ideas we have is that one of these domes will be much thicker than the other ones. So if there is a solar event, astronauts can evacuate to one location and stay there for hours or days or something like that they need to. So yes, there is some openings in, but what you do is you limit it. You don't need to close it completely. What you could do, of course, as well, is actually it is porous, you can actually throw loose regolith on top of it, so kind of to fill the holes. That's another idea that we have. So there's ways, but you never need to, there's no thing where you say like, oh, you need that much protection, and that's a static thing. It actually isn't. You need to kind of, work with that, according to how much protection you need and how long you are in those spaces. Yeah. Yeah.
Thank you for the lecture. It was very inspiring. I have a question regarding swarms. How transferable do you think swarm behaviors are in different planets? For example, you did an example for Mars, and I can imagine that these tetrapods are also 3D printed into the shape. Or how are they made otherwise? Also a question. And can you imagine the swarms also be transferring on the moon or also on the projects on the Earth?
That's 3 questions, isn't it? The swarm robotics, I've seen stuff in, there are some projects out there. I've seen similar ones, but not identical to it I've seen stuff in agriculture. I saw some projects like that. I've seen some really early design for construction. So there is some applications, but I think there are actually quite interesting applications for that. And the tetrapods, they could be 3D printed, but I actually don't care. They could be made in other ways as well. They could be maybe a small under compression or something like that, or I don't know how they would be made. That is up to other people to research as well, I think. So for us, it's never a pure technology question, right? For us, it's always related to design itself. So if we're going to build these swarm robotics, of course we're going to work with roboticists and all that. We're not going to do that ourselves. So yeah.
Thank you for the talk. It was very interesting. I have a question about the inflatable buildings. What is the time frame that you are expecting the astronauts to use these habitats? Because I was really curious about the fact that they are a holistic module. If something happens to one of them, you cannot obviously inflate another module inside one. There is things inside now. How do you fix them if something goes wrong, if it breaks, if something happens to it? Because for the cave shape, it was modular, so I can imagine you replace, or you can, theoretically. But for the inflatables, that wasn't the case. Is it because you do not expect something to happen in the lifetime that they would be used and they would be moved to a different one, or?
Well, we hope there's enough redundancy in it that wouldn't happen, right? The same thing with normal modules. Of course, in the ISS, for example, that could be a huge impact. It could happen that some debris hits one of the modules and creates a hole. It's the same thing as with an inflatable one. What you do need to make sure of is that how these modules are connected. So the way we do it is that there's always 2 escape routes from every module. And then when you escape you can still get to every other part of the base. Really important. Like we had an original design for the NASA competition where it was a star-shaped system, where we had like an extra module in the middle and then going off. Terrible idea, because single point of failure. If the middle one goes, well, they're all screwed. You know, the one that I showed, the circular one, if one of the modules goes, we can still get to every other module. The lunar base as well, we can still get to every other. So the more connections you get, the better it is, really. So yeah, hope that answers your question. Any other questions?
Yes.
Yeah, here,
Hi.
in the front.
Hey, thank you so much for the talk. It was very interesting. I have a question regarding the system with the vertical large habitat area and the inflatable one, where you put the living rooms or the rooms like mirror-wise. Do you know, like the one?
I can go back.
You mirrored the living habitats?
Yeah.
What is the advantage of this constellation with the mirroring?
Good question.
Yes.
This one, right? Yeah.
Yes.
So originally they looked at, because that is the volume. There's a shape is a shape. That's what we had. They looked at actually doing the floors like this in that direction. The thing what didn't quite work is you have this central volume that you can't even see here, where the astronaut is going in. That is a hard shell element, like a normal tubular system, right? We use that as a way for circulation, going back and front to the two spaces. The other thing is, if you're in a space and the floor just curves away, or the ceiling curves away, I know in which one I want to be, which is much more useful, right? If you're in a space that, we're used to living in spaces with domes or something like that. So it's actually much more practical in a way than having a thing that just curves away on the floor. So we think it's actually much more efficient to work that way.
Okay, thank you.
Yeah? In the back again? Yeah, or here in the front?
Okay. Hi, thank you for the presentation. It was really cool and interesting. I have a question since you are talking about the whole system. Have you thought about sewage system itself? Because we have a lot of recycling things, but what about the sewage system itself, about the water waste treatment plant and all of it?
Yeah. That of course will need to be in there. We also think that would probably be quite modular, that we don't have a system that is central, right? That you have actually local recycling happening. So we're thinking of having that each of the modules kind of working quite independent as well. So you don't have, it doesn't have to go to a super central part, but everything gets recycled quite locally in each of the modules, right?
Like a unit.
Yes, exactly. So it's a bit similar to what you have now on the ISS, right? Where these systems are actually quite localized done, and where their urine and all that gets recycled, because it'd be very important to kind of keep whatever water you have, and keep on recycling that. But we love to kind of also think about more natural systems as well, that you kind of use plants and fish and all that to kind of have more a circular system. But that's kind of more in the future as well. Yeah. Anything else? Yeah, over there. You're back.
Yes. I have a question about the walkways that you built at the top of the city, basically, the habitat. Is the reason that you are not going down inside the ground because the construction underneath the ground would be much harder and more complicated technologically, or is there a different reason, given that that obviously provides a lot of radiation protection?
Okay. Yes, you could go on the ground. You could go into lava tubes on the moon. We're not quite sure what the geometry is of that, but I think lava tubes are a very interesting thing to kind of investigate. I'd love to do a project in a lava tube, to be really honest. What we did there, if you kind of see on, let me just take one image here. Is that obvious? Which one am I going to use? Yeah, here, maybe. You see, we actually dig in a little bit. So we hope there is a few meters, or the top layer is probably quite loose, so we can actually kind of dig quite easily. Use that regularly immediately then to make all the tetrapods as well. But we're not completely going too deep, because that, we believe, would be very digging equipment would get really, really hard to start doing that. So it's kind of a trade-off in this design. But I would love to do a lava tube idea. I think that's probably one of my next ones I'm going to investigate, because that is an interesting, we have a cave already. It just depends a little bit what shape they are, how easy to get into them, and so forth. One more? Yeah?
Thank you very much for the talk. One question regarding the Mars project. You had this fancy picture there with this huge sandstorm in the background.
Yeah.
How did you consider sandstorms? Because they can take days, weeks, or even months.
Yeah.
Do I need to take a shovel every 3 days and dig myself out? Or have you done any simulations or trials even in the Sahara?
Good question. Who has seen The Martian, the movie? Who has seen that one? Yeah? A few of you. You know the beginning scene where Matt Damon gets blown away, right? That's nonsense, right? Martian atmosphere, much thinner atmosphere, but you do have winds that are 200 kilometers an hour, right? But wind pressure is particles that hit your body. If there's less particles, even if they're fast, you won't get that pressure. You won't be blown away. So yes, there are planetary storms, as you say, storms that last for weeks and all that, months even, over the whole planet. What it does do, it actually kind of brings up fine dust, right? That would, of course, be quite tricky to deal with, so they have to kind of be able to clean that. Definitely on the solar panels and all that, how to deal with that. How are we 100% dealing with that? Not 100% sure yet. Haven't quite figured that out. Yeah. Yeah.
You decided to go for the robotic system with a one-wheel configuration. It's a little funny because you
Which one?
Have the
Which
robotic configuration, the system.
Yeah.
If you put them together, it works. But
yeah, you're a mechanical engineer, aren't you? Are you? I know. I always get that question. I know. The one rover wheel is not very efficient. I know that. You put your gyroscope in there. The wheel probably need to have 2 wheels next to each other. I know that. Yeah. You probably, if you want to have one, you would probably want to have just with 4 wheels. That'd be much easier. Yeah.
Thank you.
Well spotted.
Any questions?
That's it. Cool.
If we don't have any other questions, I think Sandra would like to close the lecture today together with our guests.
Thought you were closing.
I can do it as well.
No. Usually Monica does it. Thank you very much, Xavier.
Thank you.
It was a pleasure having you here. We heard a lot of interesting, innovative ideas. I think it's very good to have an architect here speaking about future space facilities. Very important. Thank you very much. It was a pleasure.
Thank you. It was great. Thank you.